Alright, so today we're looking at quiz 3 from Organic Chemistry 2. We're covering parts of chapter 14 in here, and as usual, right, covering the material before this. So let's start breaking this down here. So question 1 asks, starting from 2-methylpropane, propose a synthesis for the molecule, right, and it says give the ideal conditions for this. So how do we get from one of these to the other? Well, if we take our starting molecule, right, we know we have to add some kind of functional group to it. At the moment we have nothing on there, so we need to add a functional group, and the only way that we can do it at the moment is by some kind of radical halogenation. And that's going to give us, let me just clean that up just a bit, that's going to give us this here, right? So now we have a tertiary leaving group, right? We got a tertiary leaving group. We got a tertiary leaving group, and so that immediately tells us, right, that in our next step, we can't really do an SN2, right? We can't do an SN2 on that green carbon there. It's too sterically crowded, so we've got to favor some kind of substitution. But we can't do SN2, so that really only leaves SN1, and right, so we'll just put, ethane thiol in there and let it do its thing, right? And at the end of the day, let me do the rest here in green. At the end of the day, right, that's what we're going to get out of it. Now, you guys should be able to do the mechanisms, right, for these two transformations. The radical halogenation and then the just a simple SN1. Right? You should know the mechanisms for those two there. But that's all I was asking for, right? Just a little simple multi-step synthesis. Okay? All right, let's move on to question 2. So question 2 is saying, just fill in the missing boxes for the following reactions. So let's take a look at what we have here at the first question, right? We've got sodium hydride and THF, right? Sodium hydride and THF. So sodium hydride. When we see sodium hydride, remember sodium is just a spectator ion. So really what we should be seeing is hydrogen with a lone pair and a negative charge. An extremely powerful base. Wow, that might be a little bit exaggerated. It's a really strong base, right? And it's going to be looking for something to deprotonate, right? So after the first step, right, it's going to be looking there for the most acidic hydrogen. And that happens to be on our oxygen, our alcohol, right? So in our first step, we deprotonate our alcohol. In our second step, we bring in methyl bromide, right? Methyl bromide. So we'll draw out methyl bromide here. Methyl bromide, the least sterically hindered leaving group that we can make, right? A methyl group, right? And so we've got a really strong base and a strong nucleophile, right? We've got our deprotonated oxygen, and we've got a good leaving group. We're just going to do an SN2 reaction here, right? Then we end up with an ether, right? So these are our conditions for a Williamson ether synthesis, right? We deprotonate an alcohol using sodium hydride or some strong base, and then we put in a primary or a methyl halide or primary or methyl leaving group to make an ether from an alcohol. Okay? Excellent. Right, moving on to the next question here, right? We have, again, an alkene, and we're making an ether from it. And now we're asked to kind of fill in the blanks, right? So we have an alkene to an ether. Again, there's a couple ways you guys could do this. I will show you guys one way, but realize, there's a couple different options that we have here. We will do an oxymercuration. So let's bring in our mercury salt. And we'll do it in the presence of our alcohol, right? We'll do it in the presence of our alcohol. So we do our oxymercuration in step number 1, right? And in step number 2, we demercurate there, right? We get rid of our mercury salt. So we're doing our oxymercuration, demercuration, and we demercurate using sodium borohydride. Okay. The other option you guys can do, or could have done, is to mix our alcohol with a catalytic amount of acid. We could do an acid catalyzed esterification. Although we could, in this case, right, we could start competing with some side products if we use that in red, but remember when we're doing chemistry on paper, sometimes we can, sometimes take a little bit of liberty here, right? But our oxymercuration, demercuration in this case seems like a viable option that we could use. All right, now we've got an ether, and now we're reacting this with acid. Question number 3 there. Remember, ethers are really resistant to basic conditions, right? They won't react under basic conditions all that much, but under acidic conditions, they'll break apart. And so our reaction here, we're basically going to split, right? We're going to split our ether. We're going to split our ether, and we're going to leave a halide in its place, right? So we're basically breaking both of the bonds, right? We're breaking both of the bonds around the ether, and we're replacing them with a halide. So we're breaking both the bonds around the ether and placing them with a halide. Here, right, at the purple carbon, we'd have an SN2 attack of our incoming halide. And let's do this in blue. And here at our blue, we'd have an SN1. Right? So go through, see if you can walk through the mechanism. That's how you get to SN1 and SN2 as you break our ether there. All right, so let me zoom out so you guys can see the first 2 questions here. Let's move on to the last one. All right. So this didn't print out clearly here. So just so it's clear here, remember we've got acid, H+, right? So we've got acidic conditions. All right, we've got acidic conditions. We've got an epoxide. The epoxide is going to reach out, grab that hydrogen. So after our first step, we have a protonated epoxide. And remember, under acidic conditions, right? Remember, this is what I call the sumo, right? The sumo mechanism, right? Under the acidic conditions, right, the epoxide is going to open, or going to start to open, and leave a partial positive at the most substituted carbon, right? At the most substituted carbon. Under acidic conditions, it's going to leave a partial positive at the most substituted. So something's got to kick open the door, right? Something's got to come in and open that epoxide. So our alkene's going to come in, hit the most substituted, and pop open that epoxide. So let's see what happens here, right? Let's go through, and let me use red here, right? So we've got 1, 2, 3, 4, and then 5 are carbon in green there, right? So we've got 1, 2, 3, 4, 5 for our carbon in green. And these are all connected now, right? That's what there it is. We made our bond in purple here, right? Whoops, that should be in purple. Right, we sent in that purple bond there. That's our alkene swinging open. We have our methyl group here, right? We've got our carbon coming off, and then our OH here, right? let me take a brief aside here for a second. Another way of doing this is, right, obviously just counting and numbering your carbons, right? And then you can go in and you can fill in what's coming off of each carbon there. Either way you want to do it, right? Use some colors, number it, make sure you don't drop any carbons along. Okay, so we're still not quite done here yet, right? Because we have to deal with a positive charge. We left behind a positive charge, and we left it behind on our carbon right here, right? That was a carbon that we swung open our double bond from. So we've got a carbocation there now. We pause, we look, is this the most stable carbocation? Do we need to rearrange? Do we need a shift? Right? We don't have any shifts or rearrangements in this case. And so we can finish things up. Our solvent, or whatever nucleophile we have, can come in. Hit that there, right? Let me just give us a landmark here, so to speak. Right, there's our green. Here's our incoming water. Right, and then the last thing that happens is more water comes in to clean things up. And we end up with this guy here, which is what the product asked us to show a mechanism for. So this is just a variation of a ring opening of an epoxide under acidic conditions. Right, our incoming nucleophile was an alkene in this case. Oops, didn't mean for that to happen. So there that is. There's the mechanism. And that's all there is for quiz number 3.